Okay, so section 1.1 in the book is now what they actually call the introduction to linear equation systems. And again, like in my own previous introduction, they start with a topic a little bit different, which you have seen in college algebra. So again, it goes back to college algebra. So where you have first only one linear equation. So we are not talking about a system for a moment. It's just one linear equation. So maybe I should write a 1 here. So for example, if you have two variables, then a linear equation example could look like this: 2x plus 4y equal to 6. This is just an example, but these are typical things you have seen before. So we have one equation and two variables, and very often the question is here to find, for example, the solutions. And I hope everyone would do here the same thing. You either solve this for x or for y. So for example, we subtract 2x, we have 4y equal to 6 minus 2x, we divide by 4, and we have 6 divided by 4 is 3/2, minus 2 divided by 4 is this. So it turns out this equation and this equation are equivalent. And now we see no matter what we take for x, this equation always gives us the y value. And for sure, everyone also knows what this is. If you plug in here all possible x values, this is just an equation of a line. So it turns out linear equations in two variables very often give us, when we like to know what is this actually, it turns out it's the equation of a line. I will not plot it, but also y-intercept is 3/2 and slope is -1/2. And then when you do here the general case, so you have something like ax plus by equal to c, and not both means ab equal to 0. So one of them, at least one of them, has to be not equal to 0. Then again, if the question is which x and y solve this, the answer is always it's a line. So there's always a line in the Cartesian coordinate system, and every point on the line is a solution, and every point not on the line is not a solution. And if both of them would be, also if A and B both are 0, then it will depend on C if you have a solution or not. But then in general, it will not be a line. So we assume that not both coefficients are 0, then we always get a line. And now you can continue this game and you look, for example, at 3 variables. So I just add a C here, kind of lazy, don't make much of a difference. So we have something like this. So now you add a C here, and now you can again bring, for example, x and y to the other side. So we have something like C is equal to 6 minus 2x minus 4y. And again, x and y can be any real number. You can plug in anything you like here, for example, 2 and a 1, and then C would be, a 1 and a 1, and then C would be, for example, equal to 0. So for every x and y, you get a C value. And again, when you think about what you get here, it turns out here, if someone asks, what are all possible solutions? What is a picture for it? The picture would be a plane. So again, here we would get a plane in 3D. And also in the general case, if you have ax plus by plus cc plus equal to d, and again, not all of them should be 0, not all a, b, c equal to 0, so at least one of them has been non-zero, then in the general case, you also get a plane as a solution. So there is a plane in 3 dimensions, and every point on the plane is a solution. Every point not on the plane is not a solution. So that's what I mean by this. And so these are what we call linear equations. And in the moment you can ask, why are they called linear? because the only things that happen is multiplying a variable by a number and adding or subtracting. So in the moment, an equation has only terms where the variables are either multiplied by number or then the coefficient time variable is added to another variable. If an equation looks like this, we call it a linear equation. And then the equation beside the terms with the variables can always have a constant term. The constant term I usually write on the right-hand side, but doesn't have to be on the right-hand side. Sometimes the constant term is also on the left-hand side. So it's always constant term plus terms where the variables only show up linear, in a linear way, where linear means multiplying by constant or adding. And whenever the constant term, or here the right-hand side is 0, we call it a homogeneous equation. So the equation is called homogeneous if the constant is equal to 0. So for example, 2x plus 4y equal to 0, that would be a homogeneous linear equation with two variables. Or if you have 2x plus 4y plus c equal to 0, that would be a homogeneous linear equation with three variables. Okay, the next step is, and that's pretty obvious, if you have an equation with 500 variables, you will not be able to write it like this. We don't have so many letters in our alphabet to write an equation with 500 variables. So what about if we have an equation with n variables? So n can be 1, 2, 3, any natural number. And so there are two problems. First, we have to find names for the variables. Then we also have to find names for the constants, also the coefficients in front of the variables. And yeah, in mathematics, there are certain conventions. So we have now n variables. And instead of saying x, y, z, we just use one letter, for example, x. But again, this is just convention. You can use any letter you like, as long as you say these are my variables. And you just give them an index, x1, x2, x3, up to xn. So these are now n variables. They're all called x, but the index shows the difference between them. Then we also have n coefficients. And I call them A1, A2, A3, up to AN. Again, that I use the letter A. Like you saw, I used already capital A for my matrix. But there's really, it's only by convention that very often coefficients are called ABC, variables are called XYZ. But there's really no other reason besides the fact historical, that's what it is. And once we have this, we can now write down an equation in n variables. So we can say something like A1 times x1 plus A2 times x2 plus ... an xn is equal to b. So that would be how we can write down an equation with n variables, n coefficients, to avoid all the pluses and the dots here. To make it more specific, in mathematics, we can also use the sum symbol. So another way of writing this is sum. J goes from 1 to n. J is now a variable which counts from 1 to n. Again, why do I use j? Now it's again because I picked j. I can also use I or k, but any letter would be fine as long as it's not a or x. And then we do aj times xj equal to b. So this is a compact form of writing one linear equation in n variables. Okay, so this is something, if you have not seen this before, you have to be able to read an equation like this. And this is the way how we write one linear equation. So now what about if we go now to a linear equation system? So instead of having one linear equation, we have several of them, and let's say m of them. So now we go from here and generalize one more time to linear equation systems. So now instead of one equation, we go to m equations. So the one equation we had like this. So this was one equation. So now I like to write another equation, and now I'm in the same trouble again, because I cannot use a anymore, because that would be already used here. So now I have to use for the second equation maybe b1, x1, b2, x2, or b would also be bad because it's the right-hand side anyway. But you see, right away we would be in trouble if we have too many equations, because then again, how would we call our coefficients? Okay, and people came up with the idea, then the a variable, just instead of just saying this one belongs to variable 1, this 2 belongs to variable 2, we make another index which tells us in which equation we are. So we write a11, a12, a1n equal to b1. So there's everywhere is a 1, and 1 means we are in equation number 1. So now we can actually write equation number 2 as a21 x1 plus a22 x2 plus a2n xn equal to b2. And now we can continue this up to equation number m. am1 x1 plus am2 x2 plus ... plus amn xn is equal to bm. So this is one way of writing now an m by n system. And the index, the first index always tells you which is the equation number. The second index tells you to which variable this constant or this coefficient belongs. And now we can again write this with our sum symbol. We can, instead of writing all this, we can write sum. J goes from 1 to n, aij xj is equal to bi. So I tells us which equation we are in, j tells us which variable we use. And so here I goes from 1 ... so still some dots left, from I to 1 to m. So this is a very compact version of writing every linear equation system with m equations and n variables. So this is the way how we can write it down in the general case. And it turns out here, these things here are already the entries of our matrix, and these are what we later call the entries of our vector. But in the moment, it's just a bunch of coefficients and variables put together, and this is how we can write a linear equation system m by n. So the next thing is some examples for this. For example, here we have 2x plus 4y equal to 6, x plus y equal to 2. So this here would be a 2 by 2 system, obviously, 2 equations, 2 variables. And I should also, I should use my own notation. So x1, x2, x1 plus x2. And so here, a11 is 2, a12 is 4, a21 is 1, and a22 is 1. Because whenever there's nothing here, it means it's multiplied by 1. And another example would be 2x1 plus 4x2. Also it's actually the same as before. 6x1 plus x2 equal to, 2. And x1 minus x2 is equal to 4. So again, how does this fit in what we have here on top? So this would be a 3 by 2 system because we have 3 equations or rows and 2 variables. So here we would have A11 is 2, A12 is 4, A21 is 1, A22 is 1, A31 is 1, A32 is -1, and maybe now I write down the B's. We have B1 is equal to 1, 6, sorry. B2 is equal to 2, and B3 is equal to 4. So here you see how this fits in the general way. And again, as before, if the right-hand side, if all these numbers are actually 0, we would call the system homogeneous. So if there would be 0, 0, 0, it would be a 3 by 2 linear homogeneous system. Also in this case, because we have 6, 2, 4, it's not homogeneous. But if all these 3 numbers would be 0, we would call it a homogeneous linear system. Just one little pitfall of the way I write it here is the following. Sometimes you have to be a little bit careful, but our systems are never so big, so there is actually usually not a problem. If I write something like A112, that is actually a bad thing, because now you actually don't know what it means. Is this for equal to A11, comma 2, means equation 11, variable 2, or is it equation number 1, variable 12? So in reality, we always should put a comma here to make clear if you have a longer number, where is it? But in most of our examples in class are much smaller. So I just write A34, means equation number 3, variable 4. But in reality, you should better write a comma. If you're in computer science, you know also if you have an array and you have to index the variables in your array, you usually have to put a comma. And the same thing in mathematics, just usually we are lazy and we don't write the comma because we assume everyone knows where the comma should go. And again, if all the right-hand sides or constants are 0, it's homogeneous. So now we go back to our linear equation system. So our linear equation system now, I just repeat what I wrote before. We have something like j goes from 1 to n, aij, xj equal to bi. I goes from 1 to m. So this is again m by n. The next thing is, what do we actually mean by a solution of this linear equation system? So what is a solution? A solution is if you have, because we go up to n, if you have n numbers, let's say S1 to Sn, and you plug them in instead of the x1 to xn, then every left-hand side has to be equal to the right-hand side. And if this is the case, we call it a solution. So a solution is, I better should say an n-tuple S1 to Sn of n, and here I like to emphasize for us, most of the time we talk about real numbers. Sometimes you can also talk about linear equations and complex numbers, but for us that will actually not happen. Most of our solutions are real, but it's only for convenience. There's no problem. Everything can be done for complex numbers in the same way. So of n real numbers, such that if we plug in S1 for x1, ... up to Sn for xn, every left-hand side is equal to the right-hand side. So this is what we mean by a solution. If you plug it in here instead of the variables, you get each time equal to the right-hand side. Okay, so, and the last thing is again a notation. So the linear equation system is called consistent if we have one or more solutions. So a consistent linear equation system means just you have a linear equation system where you know that for sure you can find one solution. Sometimes there are more solutions, but you know there's at least one. So instead of one or more, usually I say at least one solution. So consistency means there's at least one solution. And now the nice things about homogeneous equations, so if every b is 0, then for sure if you put all x is equal to 0, you have a solution because always 0 equal to 0. So this is one thing about which is nice about homogeneous systems. So homogeneous systems means all the right-hand sides are 0. Always have, this is a solution, x1 up to xn equal to 0, 0, 0. So homogeneous system always have at least one solution. Sometimes they have more solutions, but at least one solution. So that means homogeneous linear equation systems are always consistent. So homogeneous linear equation systems are always consistent. So that's a nice thing about homogeneous system. We always know at least one solution. It can never happen that they have no solutions. So this is our first little result. And this is true in the general case, m by n. So it's not important that we have only 2 or 3 variables here. Again, if you have any questions, please ask. So yeah, always, if things go too quick. Okay, so the next thing, we go back to our sandbox example where we have only a small number of variables and we check, do we already understand, do always systems have one solution, 2 solutions, or no solutions? What can actually happen with a linear equation system? In general, it looks like it's very complicated, but for the 2x2 case, which we have seen before, it seems like it's very easy. So we go to the 2x2 case and look for the different cases we have. And again, I hope you have actually seen this before in college algebra or pre-calculus, but I just like to go over to remind you what can actually happen for the solutions of a linear equation system. And